Hello friends, welcome back my YouTube channel MS Maths. In this video we are going to discuss about the equation of motion of a fluid. So equation of motion we have already discussed, we have already calculated by the Euler's equation or the simple concept of the net forces and the concept of the acceleration. Now in this particular video we will find the equation of motions or Euler equation using the vector method, by using vector method. So basically in previous one we have considered a rectangular paralleloid and using the net force along the x direction. It means we were calculating the net force along the x direction on the behalf of the surfaces which is opposite to each other, and you can follow that particular video to understand that concept of the equation of motion. So basically in this particular video we are going to discuss the this particular equation we can find by using the vector method. Consider any arbitrary closed surface drawn in the region occupied by the incompressible fluid and moving with so that it contains the same fluid particle at every instant by Newton's second law of motion. We will find something. Okay, yeah, we'll start. So if we have some surface, I can draw these types of surface in this way, and basically this is the part that is ds, or some it is the surface S, and this is the small part of this surface, and the normal vector I say for this normal for this is basically n, and the pressure on this surface is basically p, and we'll consider the small particle in this particular case, and we'll have the velocity of this particle is basically q vector along this xyz. This will be uv. Now consider any arbitrary closed surface drawn in a region occupied by the incompressible fluid, and it is moving. And now the total force acting on the mass of fluid is equal to the rate of change of linear momentum. The mass of fluid is subject to the following forces. So basically it is Newton's law that it is related to the momentum. So the the mass of fluid is subject to the following forces, that is the normal force and the external force. So normal force, which is from the normal of the fluid, and it is basically the external force, that is F, will consider later. So in this case we have, let rho be the density. Okay, so the rho be the density of the fluid within the drawn surface with dv volume and closed v enclosed v, so that the mass of fluid element is rho into v, or obviously by the density concept. Density is basically mass upon volume, that is like rho into dv. This will always remain constant. Now in this case we'll have, let the velocity is basically q vector for a fluid element or a fluid particle. The velocity of the fluid particle is q, then the momentum is m. We say then the momentum is m, and the v is basically the velocity v is basically the integration of q into this. Basically it will be velocity into mass. Okay, so this will be the value of the momentum. Okay, now the rate of change of linear momentum is given by, so basically the rate of change dou m by dou t, it is nothing but acceleration dou this is basically the v. So d by dt is that local total acceleration of the integration of q vector into rho dv. This is the formula for this. Now we can solve this by using the concept that we'll have, this is basically the integration over v, then d by dt is of basically q vector into rho dv. So for the on differentiating these two, we'll get the dq over dt, and this will remain same, that d over d, using the u into v concept. Now here rho will be the constant for this, so this is rho d by dt of the sorry for the rho. Yeah, first we have first we have differentiate q, and now we'll differentiate, so q vector will be the constant for this, and rho dv will differentiate with respect to this, is basically dv, and okay, so in this case this will be d m by dt is dq vector by dt rho dv. This is constant, so the whole term will 0. Okay. Now let this is the linear momentum is given by the basically the rate of change in momentum. Okay. Let F be the external force acting on the fluid particle P. Then the total force on volume V is given by. So the total force is basically F into m. F acceleration, that is equals to like total force is force into like mass. Mass is basically rho into dv. So let P be the normal pressure that we have already considered in that diagram at a point of the surface. We have considered any point, and the area of that surface is basically ds, that we have already considered in this way. This is ds. So then P is a normal force. It is nothing but normal pressure. Okay, it is the direction, normal direction, and P will be the normal pressure for this surface ds. Okay, then the total force on the surface S is equal to the integration over the S, that is basically pressure into minus downward, that is minus n cap ds. So the total forces acting on the entire volume V is nothing but pressure into this direction. It is basically the volume is basically del P ds. This is the relation. Okay, so this is basically V the surface and the divergence of the P. Okay, we have considered in this way. Now this relation can be used for this. This is your equation number 2, this is your equation number 3, and this is basically the equation number 1. Now we have what we can do in this way, that the integration V dou q vector by dou t rho dv by using this. Okay, so yeah, in this case if we are going inside here, this will be the partial derivative. Okay, this will be the partial derivative. Because of that we are differentiating under the sign of integration. So these are going to be partial derivatives. So dou q by dou t v into dv is equals to v f vector rho dv minus v divergence of this is v, because basically we have done in this way that equation number 3 is nothing but equation plus 1 or equation 2, and we can write in this way, this is nothing but p into f vector, rho into f vector minus dp is basically dv. Now in this way we can write the integration is basically p. F is the dq vector by dt minus we can add in this way rho dp. Like this equation we can we can find in this way, that rho dq by dt minus rho f vector plus dp into dv is equals to 0. So basically all the negative sign will go right hand side. So in this way we can conclude, or we can find, after integrating, we'll consider that rho dq vector by dt minus rho f vector plus dou p, divergence and p is equals to 0. So because this integration will 0, it means this will equals to 0. So dq vector by dt minus, or we can write in this way that f vector after dividing this is basically 1 upon rho into dou. So this will be the equation. D by dt is equals to f vector is basically we can write in this way, dou or d, sorry, d by dt is equals to dou by dou t plus q vector dot divergence. So this is the relation, we know that. Now we will use this here, this. So we have q. So q, then we will prove, like we will put q here. So we'll use this. So it will be dou q vector by dou t using this. This is the relation. We have already discussed in our previous video that q vector into del q vector is equals to f vector minus 1 upon rho into divergence of p. So basically it will be dou q vector by dou t plus the divergence of, this is basically the case we can write 1 by 2 q vector whole square minus q vector cross del cross q vector, that is curl, okay, is equals to wait, dou by t this, and this will be 1 by 2 q square plus curl of this, okay. This the relation we'll use in this case. So you on this case we'll use the, wait, next term is dou by dou q vector t plus this 1 by 2 q vector whole square plus curl of q vector cross q vector, curl of q vector cross q vector, it is basically f vector 1 upon rho dou p. So basically here we are using this as a result. So basically let me check it, dou by dou t plus this 1 by 2 q vector square minus this. Basically we are going to replace or this thing, that 1 by 2 dq dot q, that del q, okay. So on solving this equation we'll get this, on solving this equation we'll get this by using the result. Result is basically dou q vector by dou t plus del upon 1 by 2 q vector square minus q vector into cross q vector, okay. Now or this is the result. So that is del q by del t plus del 1 by 2 q square plus, we are going to consider, I think there is a mistake in this term that we have already, because omega will consider the del cross q vector is basically verticity vector, del cross q vector, and Lamb's hydrodynamic equation we want to generate here. So there is some mistake that we are going to apply this thing over here. So q vector we'll write here curl of this we want to replace is basically Del cross q vector curl we want to replace, so it will be omega cross q vector is equals to f vector is minus f vector minus 1 by rho del into p. So this is the equation. Basically we want to generate it, but yeah, there is some mistake in this step. Okay, whatever, we will we will got this equation, and this is basically the equation, that is basically Lamb's dynamical equation. So we have some contradiction in this step. Okay, so we don't want to time waste on this. Basically this is we'll use this as a result later to find the Bernoulli's equation. Okay, now we have to find the Bernoulli's equation. So basically, let's suppose body forces are conservating and flow is a potential kind flow. Q vector will be the q into minus del into phi. Phi will be phi, and omega star will be some scalar function. Then the f vector is basically minus del phi into omega star, where these omega star and हमारे पास we have q vector is basically minus del phi. So we are finding the Bernoulli's equation by using equation number A. By using equation A is basically del by del t is q. Q is nothing but del into phi plus del cross 1 by 2. Del cross 1 by 2 into q vector plus del cross this q vector cross q vector. We have this because we have considered that omega into del cross q vector is equals to minus del into omega star minus 1 upon rho into del into p. So basically we are replacing this with the force, external force, so body force is conserved, that will be omega star. These two are the scalar function. It means omega star and phi, these both are the scalar function. Now we can write in this way, let r be the position vector of fluid particle at time t. Let dr vector be the instantaneous displacement in the position of particle at this instant time t. If we multiply, if we scalar multiply, if we do scalar multiplication, equation number 3, or basically we can say that equation 3, or we can say it is equation B. So equation B dot dr, then it means we are scalarly multiply this equation with the position. So that is basically dr dot del phi. We can write in this way, is equals to dx I cap plus dy j cap plus dz k cap, that is nothing but dr vector, is basically I cap dou phi by dou x, this thing, dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z. Okay, so we can make this term as dr vector dot del phi is basically the del phi by del x to dx, del dou phi by dou y into dy, dou phi by dou z into dz. So this basically dr vector into del phi is nothing but d phi. We can write it as d phi. Now the equation number b will become minus d by dou phi by dt. We'll replace it as this plus d by 1 by 2 vector 1 by q vector 1 by 2 q vector square plus d omega star plus 1 by rho dp is equals to 0. So we can write all the terms in the derivative way, that d dou phi by dou t plus 1 by 2, these two terms we can write in this way, or sorry, plus omega will be there, no? Plus omega star plus 1 upon rho dp is equals to 0. So it is nothing but, if we are going to integrate these things, on integrating both side, so it will be minus dou phi by dou t plus 1 by 2 q vector star plus omega star q vector square, sorry, and plus integration of 1 upon rho dp is equals to some function of p, or it will be basically the constant. So we will have the cases. First, the steady flow, then the Bernoulli's equation is basically minus dou phi by dou t will 0, so it will be 1 by 2 q vector square plus omega star plus 1 upon rho dp is some constant. This is the Bernoulli's equation for steady flow. Second will be, if fluid is incompressible, then again dou phi by dou t will 0, and the integration of 1 upon rho, it is basically rho dp is nothing but p upon rho. Okay, so this will be 1 by 2 q vector square plus omega star plus p upon rho is equals to constant. Then no external body force is acting. Third case, no external body forces acting, then it will be omega star will be 0, because it is related to the it means that f0, f is nothing but del minus del omega star is equals to 0. So basically the omega star is equals to 0, so it is nothing but 1 upon 2 or vector square plus p by rho is some constant. So these all are the cases that we have discussed, that are the Bernoulli's equation and Lamb's equation. By the vectors method we have calculated. So thanks for watching my video. Keep watching MH Maths, and for these types of video you can follow my channel. For higher mathematics you can follow my channel, subscribe the channel, like the video and share. Thank you. Bye bye.